Hello everybody. So today we're going to have a bit of a longer talk because we're going to go pretty in depth on this next cycle. But before we get right into it, what I want to do is give us a brief review of where we've come so far with cycles. So if I was going to draw a quick sketch of like the cycles that we've studied, we have the ideal work cycle and we have the Carnot cycle. Those are both considered simple cycles because of their shape. In the TS plane, the Carnot cycle is a rectangle, and in the PV plane, the ideal work cycle is a rectangle. And then we talked about the fact that if you were looking to like split the difference or come up with cycles that are sort of the best of both worlds between the ideal work cycle or the Carnot cycle, well, you could either flatten in the sides. So you would make the vertical sides isochoric, like the ideal work, or you could flatten in the top so that you would make isobars, like the ideal work, and the other sides that you haven't flattened would be like the Carnot cycle. And the two cycles that we saw for that were the Stirling cycle and the Ericsson cycle. Okay? So those are sort of, that's how I think of it. They're sort of meet in the middle cycles. Now, last time, we brought up the fact that for the Stirling cycle, we had this weird phenomenon where people mixed up the Stirling cycle, the Ericsson cycle. People mixed up the Ericsson cycle with the Rankine cycle. And I'm going to draw a quick sketch that I'll erase. But the problem was that for the Ericsson cycle, we had a shape that looked like this, and for the Rankine cycle, we had a shape that looked like this. Make sure I draw it right. And so this is why people confuse them. This is the shape in the PV plane. But we talked about the fact that the difference comes in what these curved lines are actually following. And if you'll remember, for the Ericsson cycle, write an E for Ericsson. For the Ericsson cycle, these curved lines were isotherms. So they followed those green curves, which are isotherms. And of course, we know that the equation along an isotherm is simply something like P equals a constant over V, and V was to the first power, okay? For the, let's see, this is Ericsson. For the Rankine cycle, I'm going to write this sort of a squiggly arrow down here to show this is the one that had the same shape that people got confused with. So now I'm going to draw the Rankine cycle here, and I'm going to try to draw in some isotherms. And what we notice is that what's actually happening here is that these curves are jumping the isotherms, or they're skipping between them. Those are adiabatic processes, but not isothermal processes. So even though they're similar looking in shape without any context, once you give it a little context, you can see that those curves are different. And to finish the comparison here, remember that the curve here was a constant over V to some power, and that power was CP over CV, okay? So that was the difference, but people got them mixed up. That same story is actually the introduction to the cycle that we're going to do today. You see, there's the Stirling cycle that we have here, which looks like this. We talked about it last time. It's got the vertical walls, and then it's got the isotherms along there, and then I'll sketch in another one, and you can see where we're going. Okay, so this is S for Stirling, and here along the top and bottom, this cycle follows isotherms using P equals constant over V. There's a new cycle that we're going to study, which is a similar shape, and so I guess you could get confused. But what happens with this one is that, like the other one, these are isentropes, or lines of constant entropy on the side, and they skip over the ice, they jump between isotherms. So there is a temperature change there, okay? And that cycle is called the Otto cycle. All right? That's my introduction to how that fits into the scheme that we've been looking at. All right? So I'm going to raise this board. And we will start looking at the Otto cycle. Now, the first thing that I want to mention about the Otto cycle is it's different from all the cycles we've looked at thus far in a very fundamental way. Usually, the implementation of the Otto cycle uses what's called internal combustion as opposed to external combustion. And here's the difference, okay? The ones we've been looking at are external combustion, and we have a system, and that line, actually this is going to need to be bigger. This box represents our system, and this is the system boundary. So here's the surroundings, and here's the system. So this is, in the system, the working fluid. I know that we've used that terminology before. That can be a liquid, a gas, the fluid that's actually undergoing the thermodynamic process that we're tracking as we write the process paths in the different PV and TS diagrams, okay? And so maybe in our application that's going to be air, all right? It could be any fluid. And the heat is coming from the surroundings. So the heat source is outside of the system boundary, and in order to get heat in to the working fluid, it has to cross the system boundary. That's the really important point, okay? That the heat source is outside. That's why it's called external combustion. Most traditionally, the heat source is combustion, even most of these engines still today, and so that's what they're referring to, that the combustion happens outside. Well, as you can imagine, we can contrast that with internal combustion, which has, again, the working fluid inside the system, but this time, the heat source is also within the system. And so it's like you're heating up the system from the inside. Thus, internal combustion. The combustion is happening right mixed in with the working fluid. You're not able to separate out the heat source from the working fluid. The downside to this type of system, an internal combustion cycle, is that the heat source has to be something renewable, right? So here, we can keep our system all nice and pretty and like locked up. Like this is our system, it's locked away. And we can keep cycling through heat, whether we're burning coal or burning gas, we just keep burning it, bringing it in, burning it, bringing it in, burning it. But the fluid is not affected. That just stays in its nice little box of the system. Here, because the heat source is inside the system, the material, the actual physical, whether it's gas or liquid, inside the system is constantly needing changed out or recycled. Because we need to keep getting a source of energy in there to keep getting heat transferred into the working fluid. And so this has to be like, okay, we do a cycle and then we replace all this, working fluid and heat source, we replace it. And then run a cycle and then it's done. We get it out and replace it. And so the actual working fluid itself requires replacing. So now that we've made that distinction, the inventor of the Otto cycle, we can name him. His name is Nicholas Otto. And let me see if I can get his name spelled right. Nicholas. It's like an old spelling. Nicholas Otto invented this cycle, and the reason why it's so famous is because it's used to model gas automobile engines. That's why we're going to spend some time on it. So the thermodynamics of what's happening under the hood in your gas car or truck is described by the Otto cycle. Now, I was watching a video by a physics professor who just must have been mixed up about his facts, and he said that's why they're called automobiles, because they're using the Otto cycle, so automobiles. That has no connection whatsoever. The auto in automobile is from a completely different language actually, and it means self-propelling, okay? It's just a coincidence, and it's an easy thing to remember that the cycle that goes with the automobile is the Otto cycle, okay? It really is just one of those coincidences of history. So, let's try and describe what the cycle is like we've done before, okay? So I'll draw up, maybe a little smaller this time, save space here. I'll draw up my PV and my TS diagrams. So this is pressure versus specific volume. This is temperature versus entropy. And I want to plot out the cycle as it goes. So, the first process, oh, and I've got to label state 1 on each one of these. So, state 1 starts about down here and about down here on these guys. So from state 1 to state 2, first thing we do is we do isentropic compression. Now, before I even go drawing anything, remember that the line on the state diagram for an isentrope is the perfect version of an adiabat, or a line of no heat change, okay, adiabatic, right? So in practice, this is more like adiabatic compression, and all that would mean is that it gets a little more complicated because, well, I can write again what this is. It's isentropic, so we're going straight up, state 2. In the real world, it would be a little bit skewed from that, and that would be adiabatic. The line on the PV diagram for an adiabat is going to look very similar to an isentrope, okay? So we model it as, again, ideal or as perfect as we can imagine it, which is isentropic. So we've got this isentropic compression, and on this diagram, isentrope, that's going to be that line that comes up here like this. And forget what it's called, polychoric or something, is described by that shape that we talked about, which is P over V to the CP over CV in the exponent, okay? Next step, going from 2 to 3, we have isochoric heat addition. So, isochoric, that's easy to do on this one. That means straight up, straight up on this diagram. So from 2 to 3, at some volume down here, this is V2, and then the volume where it started is V1, okay? So then we're going straight up. Now, this is the heat addition step. I'll draw it over here too. Remember, we have that exponential curve for this. This is state 3. And I'll draw to indicate that the heat is added during this step, like we like to do, in blue to keep it consistent with the other lectures. Q in is happening during that step from 2 to 3. Then from 3 to 4, we have isentropic expansion. Now I'm going to, even right here, make a very important note. This is the step where the work is done by the gas, and we will definitely be coming back to that in just a second. So isentropic is easiest to do first here. We come down to 0.4 like that, and here we have another isentrope, so we're coming down something like this to state 4. Okay, and then the final step of the process, 4 to 1, wasn't a very good arrow, is isochoric again. Heat rejection, or removal, okay? And we're coming down, dropping straight down from 4 to 1, and again, this is another isochore on here, so it's the exponential curve coming back. That's the step where heat is removed, so we can indicate that, Q out during that final step. Okay, so I've described to you the thermodynamic cycle and what it looks like, just like I've described all the other thermodynamic cycles. But what we really want to take a look at is take a little extra time and talk about what's happening inside the engine on each step of this cycle. Because we're going to get into how these steps of the cycle relate to the different strokes of the engine, all right? And turns out to be pretty interesting. So let me draw a divider line right here. Okay, and then down here I'm gonna start to draw some diagrams of what the inside of the engine looks like. Now, we all know that, or I hope we know, that in an engine cylinder, a piston cylinder inside an engine, we have something like this, and we have a piston that I'll draw in. That's the rectangle at the bottom. The top is sealed off most of the time, okay? There's a piston down here at the bottom, and there's some volume that the piston can encompass. And so this is like it's sitting in state 1. So that means that, notice how in state 1, it's up at its highest or maximal volume, right? It's as full, the piston's all the way lowered. So this whole area is as full as it can be of the working fluid, which is air. And we'll also find there's a mix of fuel in there because it's going to be internally combusted. So the heat is going to be put into the air from the inside of this, okay? But we've got a working fluid right here filling up the total volume. Now, this piston has moved all the way to the bottom of the cylinder. And when I say bottom, I don't mean it in any sense of a graph or anything. I mean it in the geometric sense, literally top to bottom. It's at the bottom. So this down here is called the bottom dead center. That's a label for a volume. That amount of volume that's in that cylinder when the piston is at the bottom is called the bottom dead center. Like, it's so specific for an amount of volume that I can replace V1 with the label of bottom dead center, okay? That's a way of writing that V1 volume, or the maximum volume. Now, what's happening during the cycle from 1 to 2? Well, it's compressing. So what happens, I'll try and stand over here, is the piston rises up. How does it do that? We'll talk about that in a minute. But it rises up. Can't go all the way because there's some working fluid still in there, right? I'm going to draw a cloud up top. It's been compressed. All that fluid that was in there has been compressed up until a small amount. So it can't completely close, otherwise the fluid won't disappear, but it's going to get really small, the amount of volume. As you can imagine, if this is bottom dead center, this position up here is called top dead center, and that's another volume. That's showing as it compresses, the volume gets smaller and smaller, right, along this axis, smaller and smaller volume, until we get to here at state 2. So this is where the top dead center goes, okay? Now, because it's compressing, you can even see it in our description, isentropic compression, this is called the compression stroke. All right? So I'm going to label all of the steps that we've got. That's the compression stroke. And I'm going to label it right here with just a bracket. 1 to 2 is the first stroke. That's what the bracket means, what a stroke is. Now, there's heat added. The way that the heat is added in an Otto engine is that there's a spark plug up here at the top of the cylinder that gives a spark, and that ignites all of the fuel-air mixture that's compressed in here. That happens effectively instantaneously, right? Compared to the full stroke up here, and then we're gonna have a stroke back down. Compared to the amount of time that those strokes take, that ignition and that heat, it goes from low heat to high heat almost instantaneously. And so that's not considered, that heat addition step is not considered to be a stroke of the engine, if that makes sense. So we'll either leave it out, like this heat addition step here won't get a bracket, or sometimes you'll see people maybe extend this bracket so that they include both of these top 2 steps as part of the first stroke, or stroke number 1, the compression stroke, okay? So moving on, what's the next thing that happens? I'm gonna draw out the cylinder again. Well, the piston starts up here at the top, and it travels back down to the bottom because it's pushed down to the bottom by all of the energy in that expanding fuel. The energy, the work being done is actually coming from this fuel right here. It's got chemical potential in it, which is immediately burned off and shoves that piston back down. So this goes back down like that, and I'm gonna draw a little explosion to indicate that's what's making it go down. This is where the work is done. Notice that we're on this step, and I said we would talk about this. This is really crucial. The isentropic expansion step is the work done. And normally we care about, obviously we can do any amount of work in give us long enough. So the thing we actually care about with an engine is how quickly can we get it done. So it's power. That's why this is called a power stroke, okay? This is the step, and as you'll see, it's the only step in the whole process. This is the one step where we actually get power out of the engine, okay? When this explosion forces the piston back down. So here's a bracket to indicate that that's a stroke. Now, by drawing the next cylinder, what we have now is the piston is sitting at the bottom, at the end of the power stroke, and it's actually going to rise back up. Now, I'll draw it in where it rises back to the top dead center. Now, what's in here? Is there an explosion? Is there fuel? No, there's like charred remains of fuel. So I'm just going to draw some of these things. I guess they wouldn't be in here, would they? Yeah, well, I can draw it at the bottom as it's rising up, right? So this whole capacity at some point is filled with these little dots or circles that are basically the spent remains of the fuel. They're not good for producing more energy, but they're just there, and we've got to somehow get rid of them. So this piston rises back up. Now, what causes that piston to rise up? It's actually inertia. We'll talk about that once we get through the whole cycle, but this piston is going up and down really fast. In real life, this cycle runs incredibly fast. And so it's gone up here, it goes down here, I should say up arrow. So it goes up here, it goes down here, and then the inertia of that up and down causes it to rise back up. That's purely what it's doing. There's no force, there's no other force here in our picture causing it to work other than that kind of inertia, all right? Turns out it's inertia in the flywheel of the engine. This step is called the exhaust stroke. Now, I should also note, you know how we put the heat addition kind of with the compression? Well, some people lump the heat rejection with the expansion, because as the power stroke comes down and does work, and this expands, we lose that heat from the explosion. Obviously, the energy is being transferred. So, now we've got, we said an exhaust stroke. And the question is, where on our diagram does that go? So let's talk about this for a second, because we've already made it through our whole thermodynamic cycle. Here is where the thing that I mentioned at the beginning about the difference between external combustion and internal combustion comes into play. Remember that with internal combustion, we can't just keep using the cycle on the same air or the same working fluid, because when we're dumping the heat source in there, it's spent. This mixture in here is spent. It's all out of juice. It's not going to provide you any more work. So we somehow have to get rid of it. The way we get rid of it is we have the valve here, the exhaust valve, open up, and that's on the timing belt, and so it knows it's timed with the piston and it knows when to open. And so as this piston rises, it pushes all of that exhaust or spent fuel that's already been exploded out of the cylinder. Okay? Now, where does that fall on this diagram? It actually happens like this. It's an isobaric process that, again, we decrease the volume. Okay, so it's going from bottom dead center to top dead center. As this thing rises, the volume shrinks as the exhaust goes out. Now, why is it isobaric? Or in other words, at constant pressure over here on the pressure axis? Well, that's because any time that we open up a valve into this chamber, we're going to model it as pressure staying constant. That's because the only thing that can pressurize this chamber is its like sealed boundary. No gas can escape. So if we move the piston, we're changing the pressure, like in the rest of the cycle. But now, gas can escape. That's the exact purpose of it. And so whatever pressure is in the pipes and valves and stuff, the system outside of here, that's going to equilibrate. And it's going to allow, as this piston rises, it to do it at a constant pressure. So that is the exhaust stroke. And it's modeled going from 1 to, we have a new point. And what do I call that point? I've already got a complete cycle, 1, 2, 3, 4. So let me call that point 0, okay? And that is the exhaust stroke. Now, we've got a cylinder that we've just ejected the fuel air mixture out of, the spent fuel, and we need to refill it so that we can start the cycle over again. Because we started the cycle with the piston down at the bottom, but a chamber full of the air with the fuel mixed in. So this is the step where we fill it. It's called the intake stroke. And what happens is the piston goes from top dead center down to the bottom dead center, and behind it, it fills up with fuel again. Okay? And I drew a little squiggly arrow here to show that it's being exhausted, and here there's a squiggly arrow to show that more fuel is coming in during that step. Again, what causes it to go down? Well, the same thing that caused this to go up, which is inertia of the crankshaft. Okay, the flywheel on the crankshaft has inertia, and that's what's causing this to happen. So, during the intake stroke, we're going from low volume, or top dead center, down back to large volume, or bottom dead center. And again, since this valve is open, it's constant pressure. So where do we plot that on this diagram? We're at 0, constant pressure, change of volume. Well, we just go back to state 1, like that. So this is the complete cycle diagram for an Otto cycle. There's this extra point 0, and there are these 2 extra process paths that lie directly on top of each other. It just travels one this way and one that way. All right? And so some people, if you've seen these presented in a different order, you might have seen the intake stroke presented first. Obviously it's cyclic, so it doesn't matter what I count as the first stroke. They all keep going. But that's because some people start imagining the process as they start at 0, whereas we imagined it as starting at 1, going around, and then doing this. This extra step right here, again, the back and forth from 1 to 0 and back, is only because we need to refill this thing with fresh heat source. We've got to get rid of the old wasted and refill it. It's a product of the internal combustion. So did I get everything on that? I think so. So now let's talk about the difference between a 4-stroke engine and a 2-stroke engine. Because what I've described here is a 4-stroke engine. So the difference with a 2-stroke engine is that they decided, well, that seems like a waste, that going back and forth like that. So what people realized you could do is you could eliminate that step, this isobaric back and forth. And so you could essentially eliminate these 2 strokes and only have the compression and power stroke, okay? Just these 2 back and forth between each other. If you could somehow find a way to get the fuel out of the chamber and get new fuel into the chamber while that's happening without having dedicated strokes for it. And so instead of valves at the top, there's a thing called a port. There's an intake port and an exhaust port, and they are clever pieces of engineering that allow you to run just these 2 strokes back and forth while the fuel comes in and out at the same time. That, again, like we talked about, eliminates, I'm not sure what color to use, but that eliminates these steps. So for a 2-stroke engine, it's only what's in green. You don't have to do this back and forth from 1 to 0. We'll come back to talking about 2 strokes in a little bit. The other thing is this question of where does this inertia really come from? We're back to the 4-stroke engine here. On these 3 steps, really, this one, and this one, the piston is moving, and there's no obvious reason why it should be moving. Here, obvious. This is the power stroke. This is where the piston's being driven downward and creating work by this explosion. So why is it moving in the other 3 steps? I mentioned that there's the flywheel on the crankshaft that keeps this going, and that's inertia. And that's the explanation. That's not a lie or anything, but here's how engineers have designed motors in order to help out that flywheel. There are, let's first imagine 4 cylinders. So this thing is happening in 4 different places, physical locations within the engine, and they're all connected to the same crankshaft. So if you time it right, and they do time it right, then you can have one of your 4 cylinders always executing a power stroke. Well, the other 3 are in one of the various other 3 stages where they need help actually moving their piston. It's always one of them that's actually providing the power, which is just an ingenious design. So that's a four-cylinder engine, and that's the basic explanation why most engines have more than one cylinder. There's also the 8-cylinder engine, which means that it's just the double of the 4, and so you have 2 of the 8 that are at any stroke providing the power stroke. And then there's the 6-cylinder engine, which sort of splits the difference and does something more complicated that's in between what the 4 and what the 8 does. Okay? So why don't we may have to come back to this board, but so that I get more board space, I'll raise this, and we'll go into talking about the work from the Otto cycle. So I want to remind you for a second of this little sketch that I made, how the Ericsson cycle can be confused with the Rankine because they have similar shapes. Well, it turns out that if you look back at your lab specifically, I don't think it's in the Rankine cycle video, but it's in your lab that we did. Using the Brayton cycle, this should really be Rankine/Brayton because we've learned the difference, okay? So in that cycle, we used a work formula, and then in the video for the Ericsson cycle, I gave you the work formula. You might have noticed that they're the same. I'm sorry, no. It's the Stirling and the Ericsson cycles that are the same. So these two have the same work formula, and we remember that they both have the Carnot efficiency. So same work, same efficiency. These two also have the same work, same efficiency. That's what we're getting at. So if you remember back to your lab, the work formula that you did for the Rankine/Brayton cycle, well, that's the work formula for the Otto cycle, okay? So I'm just gonna write it down, but realize that connection. And as we'll see, it actually turns out that the efficiency is the same as well between the Rankine cycle and the Otto cycle. So there's this connection sort of crossways as well between them. Okay? The work net from the Otto cycle is CV times this thing that's like a difference of differences. So T3 minus T2 minus T4 minus T1. Okay? Hopefully you remember that. Efficiency of the Otto cycle. Well, we know that we can start out the efficiency with 1 minus Q low over Q high, okay? Or Q in over Q out. So, or did I say that backwards? I want to make sure I didn't say that backwards. We can look at our graph, that's what it'll tell us. Q in, the temperature change was from 2 to 3. You can see that better on this temperature plot right here. Q in, the temperature change was from 2 to 3, and Q out, the temperature change was from 1 to 4. So I'm just checking that. So Q out over Q in. Not sure what I said before, but that's how it should be. This is MC. Now remember this, we have MC delta T, that's our formula for the heat here for any ideal gas. We want, because it's a gas, to distinguish between CP and CV. And we know that this was a process that happened at constant volume. So we're doing CV. And then our delta T for leaving is T4 over T1. And here on the bottom, we have the same thing for the incoming, which is T3 minus T2. Check that with your notes of what's up on that board that's hidden right now. That's what the temperature differences were for those two processes, where there was heat in and heat out. This thing can be further refined by canceling the MCs. So first, I guess I can do this. 1 minus T4 over T1, T4 minus T1 over T3 minus T2. So I can cancel out those things in front, they're the same. And then there's a nice realization. The first step we'll have to do before we get to that realization is factor out a T1 out of this whole thing, top, and then factor out a T2 from the bottom. So it looks like this. T1 over T2 times T4 over T1 minus 1 over T3 over T2 minus 1. So notice how that is the exact same expression than that. If you're having trouble seeing the algebra, you can believe me, but imagine putting it back. That'll help you see it. Imagine putting the T1 back in the top and the T2 back in the bottom. You would get back to this. Okay? And then the final thing, here's the realization that you make, is that, I want to make sure I get my terminology right here. The isentropic relationship for an ideal gas, I'll write that here. Tells us, this is back when we studied entropy, that T4 over T1 is equal to T3 over T2. Those two ratios are equal to each other. That means that this entire thing cancels. Everything in the parentheses cancels out. So we're left with a nice formula, 1 minus T1 over T2. Okay? So that's the final form in terms of temperatures of the Carnot efficiency. There's all the work for it, if you need to see it. Turns out that it's often not nearly very practical to measure the temperatures of a cycle inside an automobile engine, right? There's nothing wrong with that formula. It's not mathematically wrong. It's just practically not very useful. The thing that we measure inside of the automobile is the compression ratio. Hopefully you remember the compression ratio. So first I'm going to write down what the formula is in terms of the compression ratio. It's 1 minus R to the 1 minus Cp over Cv. So that formula is not that bad to remember. And then I'll remind you that R is the compression ratio. Okay, and what that meant was that it was the difference between V1, the maximum volume, and V2, the minimum volume. This is worth pulling down again just so that you can visualize this. V1 was over here, and V2 was here. So you notice that as this cycle moved, it actually, again, had 4 strokes. So it compressed twice and expanded twice. Compresses to 2, expands to 4, compresses to 0, expands to 1, right? Compressing and expanding between these two volumes. And that ratio is R, the compression ratio. It also can be written as the ratio of bottom dead center over top dead center, because those are just other names for V1 and V2. So, I'm not going to show the work behind that, this thing turning into that thing, but you can do it, all right? So this will be a more useful form of the efficiency for the Otto cycle. Okay, what is the compression ratio? I'll do that in parentheses as well. For a gasoline engine or an auto engine running an Otto cycle, it's typically around 10 to 14. That's the value of R, okay? Anywhere in that range. Now, how much more do I have to discuss? Another note while we're talking about the volumes. This is not really related to anything other than it's interesting. when people talk about engine capacity, that's like if I have a truck, like a 5.4 liter truck, okay, that's our engine capacity. And that's the total of all of the displaced volume within all the cylinders. So we can write down a formula for it. If we think about the displaced volume, what's the difference between the volume when it's at the bottom and it's completely full, and when the piston rises to the top and it's as smushed as it's going to be, or the maximum volume minus the minimum volume. So this is bottom dead center minus top dead center. I wrote the wrong thing and said the right thing. So that difference, and then again, the engine capacity is this times the number of cylinders, because it's the total of all the cylinders. So this is the number of cylinders. So maybe I'll throw in a nice easy question for you guys about the engine capacity if I give you bottom dead center and top dead center. That's just an interesting, like, another real world connection that you hear with advertisements on TV about trucks and cars and stuff like that. Okay, what else do we have? The other thing we want to remember is that when we're dealing with engines, we're dealing with power. So the thing we really care about, I'll write that up here, another reminder, is the horsepower, or in SI units, that would be watts for units of power, and that is W dot, which is the work divided by the time interval. So we can write efficiencies with the powers instead of the works, right? Typically we use like a heat in minus heat out over work, but you could dot everything and do a dotted or a time dependent version of the efficiency. So as we think about how the time dependence here to get the power out affects the different efficiencies, let's have a talk about the efficiency of a 2-stroke versus a 4-stroke engine. So one interesting thing to do is maybe take a minute before I go into the answer and think about what you think it is. Which one do you think is more efficient between 4-stroke and 2-stroke? Remembering that the difference was that additional isobaric step back and forth for the intake and the exhaust strokes. The 2-stroke doesn't need that, whereas the 4-stroke does need that. So which one's going to be more efficient? Well, I'll make a chart here. 4-stroke, 2-stroke. As a reminder, the speed of the 2-stroke, like how fast does each cycle go around, that's going to be measured by the RPMs. This is literally like when you're looking at your dashboard, reading the RPMs of your engine, that would be the RPMs of your 2-stroke, because every time the piston goes up and down once, which happens in a complete cycle for a 2-stroke, the crankshaft is going to turn one time. For your 4-stroke, you're going to actually be doing 4 strokes or 2 turns of the crankshaft per cycle. So the speed of a cycle can be measured by the RPM divided by 2. Okay? I hope that makes sense. You have to divide the RPM by 2 to get the cycle speed, because the cycle is happening slower than the crankshaft is turning. It's happening twice as slow. Now I'll write down the thermal efficiency, or the formula that we have over there. So efficiency of the Otto cycle, thing we've got over there. It turns out that because of this difference in the speeds, the extra 2 strokes, those of you that guessed the 2-stroke engine would be more efficient are right. These are hypothetical numbers. I do not promise that these match up very well with real world estimates, okay? So hypothetical numbers. let's say that the two-stroke engine was 80% efficient and the four-stroke engine was half that, because you have to half the RPMs. So it's not getting as much done. Well, that makes sense, and that will be our thermal efficiency. I want to emphasize that this is given by thermodynamics. Now, the problem here is that the story is not quite that simple, because there's other systems in your car. In particular, in this chart, the other systems that we want to focus on are the differences between the valves in a four-stroke and the ports in a two-stroke. And again, these other systems efficiency, that could be from lots of other things. We're just going to think about this difference. If you have the valves, they're sealing off that cylinder when they're not open or closed. It's a very tight fit, and everything works very smoothly. And so it turns out that the valves have an efficiency with them, or could bring an efficiency of, let's say, 75%. Whereas the ports, because they're trying to inject fuel and exhaust the wasted fuel at the same time as everything else is happening, there are plenty of losses. They can be open to the air, you're losing pressure, you're losing heat. That's what the ports are one of the reasons why the two-stroke engines have to have the oil right mixed in with the fuel, because everything needs to be so much more oiled up. It's way less efficient. That part of it is way less efficient. So let's say that that part of it has an efficiency of like 0.25. Now look what happens when we go to get the total, or the overall efficiency of the engine. Well, we have to multiply these two effects, the thermodynamic efficiency times all the other systems. And for a four-stroke, we get an efficiency of about 0.3. And that number is actually researched. That's about right. For a four-stroke Otto engine, we're getting about 30% efficiency. And you may think, oh, it's 2020, why can't we do better than that? Well, we can do a little better, but not much, okay? I still think we haven't broken 50%, for example, even with all the modifications that we'll talk about in future videos. For the two-stroke, again, we'll multiply these and discover that the efficiency there is about 0.2. So I want you to use this chart anytime that in your life that you come across a confusion over which is more efficient. Notice that thermodynamically, the two-stroke engine is more efficient than the four-stroke engine. And so you'll hear some people say, yep, two-stroke's more efficient than four-stroke. That's the thermodynamics of it. But because of this difference, once you get to the overall, the four-stroke becomes more efficient than the two-stroke. And we did a whole video about this, talking about how different people mean different things when they say the word efficiency. And so if somebody says, oh yeah, the four-stroke's more efficient than the two-stroke, don't let it confuse you. Oh, I thought I heard the opposite. Okay, because it can be very confusing because you hear people say both. Well, one group's talking about this, and the other group's talking about this. So just note that difference. Okay, I think that's been a pretty comprehensive overview of the Otto engine. So next time we're going to talk about some of the things that people have done to the Otto engine to make it more, to improve the efficiency of it, or improve it in some other category. All right, so I'll see you soon.